Okay, so we're going to do the second part to the lesson on planes, and this is going to be about the Cartesian plane of a Cartesian equation of a plane. Okay, so first we're going to let n be the normal vector to the plane, so it's a perpendicular vector to the plane. Okay, so just like we had when we had the Cartesian equation of a line, we had a normal vector to the line that was AB. Well, now we're letting the normal vector to the plane be ABC, because it has to be in 3 dimensions. Okay, P naught is some fixed point on the plane. Okay, so we know the values of x naught, y naught, and z naught. And x, y, and z are going to be any point on the plane. Okay, so when we draw that out, we get a nice picture that looks like this one here. Okay, so P naught, some point on the plane, N is perpendicular to the plane, and here's P, which is any point on the plane. So from this, hopefully you can see now that we're going to use the same strategy that we used when we got the Cartesian equation of a line. So P naught P is a vector from P naught to a point on the plane, and this vector, because it's on the plane, is going to be perpendicular to the normal vector. So no matter what you choose for P, P naught P dot product with N is going to give you 0 because they're perpendicular. Okay? And so we're going to check that out. So P naught P is perpendicular to N for any point P on the plane. This means that N dot P naught P equals 0. P naught P, if you recall, is the vector x minus x naught, y minus y naught, z minus z naught. Okay, just by taking the coordinates of the points. So P naught P is OP minus OP naught. Okay, so the coordinates of point P minus the coordinates of point P naught. Okay, when we plug that into the dot product, we get this nice expression here. We multiply that all out, and we get this one. So A times the x coordinate, B times the y coordinate, and C times the z coordinate. We can simplify that one more step. We get AX plus BY plus CZ minus these constant terms. Okay, so AX minus AX naught, so I put it over here. And the reason I'm putting the minus AX naught over here is because that's going to be constant. We know A and we know X naught, so those are constant values. BY minus BY naught, that's a constant value, so I'm putting that over there. CZ minus CZ naught, so CZ's here minus CZ's not here. Okay, all that still equals 0. These are the variable terms, so I'm going to keep them over here. These are the constant terms, and because they're constants, when you multiply it all out, we're just going to let that equal some letter D. So just like in equations of the line, we had C was the combination of some multiplication of constants. Well, we're going to go extend one further here. Now we have C in front of Z, so we need D as the constant term. Okay? So this is the equation, Cartesian equation of a plane. Okay? Now, moving on from that. Okay? Well, we can write it out like this. So AX plus BY plus CZ plus D equals 0 is a Cartesian equation of a plane with normal ABC. So we can't forget that. The normal to this plane is ABC. So these coefficients of the variable terms produce a vector that is perpendicular to the plane. So in the parametric and vector form, we had 2 vectors that were parallel to the plane, or span the plane parallel to the plane. Okay, so now we have a vector that's perpendicular to the plane. There is some relation there, so we can say that those vectors that are parallel to the plane will be perpendicular to this normal vector, and so their dot products must be 0. Okay, so we've got to keep that in mind when we're doing some of these questions here. All right, so using that, let's jump to the example, first example that I've got here. Okay, determine the equation of the plane that is perpendicular to n, 2, negative 1, 7, and contains the point 1, 2, 3. So you might want to pause the video now and give it a shot before you look at the answer. Okay, so 2, negative 1, 7 is the normal vector and the coefficients of the variables, so it's a, b, and c. So we know that the partial equation to the plane is going to be 2x minus y plus 7z. The 2 goes there, the minus 1 there, and the 7 there. It's a, b, c. And then plus d equals 0. So how do we find this d? Well, we've got a point. So we know values for x, y, and z that have to satisfy this equation. So let's plug them in. Plug them in, and you'll end up getting d equal to negative 21. Once you got that, you're done. So the equation of that plane is 2x minus y plus 7z minus 21. There's the d value. Okay, is the equation of that plane. Okay, so one thing I want you to try now for homework is, what if I gave you just this equation of the plane? Okay, so you don't know any of this other information up here, you've just got the equation of the plane. Now, how do you convert that to its vector or parametric form? Okay, so what are you given just by looking at this? Well, I'm going to give you a bit of a hint. 1, you know the normal vector. 2, negative 1, 7. Okay, well, in the parametric equations, you need a vector that is parallel. You need 2 vectors that are parallel to the plane. Well, if you've got a vector that is normal to the plane, so 2, negative 1, 7, how do you find 2 vectors that are perpendicular to that? Okay, so you've got the plane looks something like that, and you've got a normal vector to it. Okay, how do you find 2 vectors that are perpendicular to that plane? Well, one method I have was to flip 2 of the coordinates, so take the negative reciprocal of 2 coordinates and make the third one 0. So one vector would be 1, 2, 0. Another vector could be, let's flip the second, last 2, 0, 7, 1. Okay, so that would give you 2 direction vectors. Then, once you got the direction vectors, then you need a point on the plane. You need some set of x, y, and z that makes this equation true. Okay, if you needed a point on a line before, you would choose an x, solve for y. Well, what do you do here? You can't just choose an x. You might have to choose more. Okay, so you need to find a point on that plane and direction vectors, and then you can get the parametric and vector equations of that plane. Okay, so you need to try and finish that off. Okay, so the next example, example 2, determine the Cartesian equation of the plane with this vector equation. R equals negative 1, 2, negative 4 plus S times 1, negative 1, 2 plus T times negative 3, negative 2, 1. Okay, so you want the Cartesian equation of that plane. Well, you know 2 direction vectors for that plane. And you know a point on that plane, so P naught comes from there. Direction vectors from here. You need a normal vector. You don't need vectors parallel to the plane. You need a normal vector. So maybe now you might want to pause and think about how you're going to do this and try it. Okay. So hopefully maybe you've come up with the fact that the normal vector has got to be perpendicular to both these direction vectors. How do you get a vector that's perpendicular to 2 vectors? Cross product. Okay, so cross product those 2 vectors and you get 3, negative 7, negative 5. And this is going to be good enough for your ABC because it's perpendicular to the plane. Okay, sub those into the equation, just like before, 3x minus 7y plus 5z plus d equals 0. A, B, C go in there. And sub in the point P naught to solve for d. Sub that in. D equals negative 3. And the equation of the plane is 3x minus 7y minus 5z minus 3 equals 0.